Okay, let's get started. Okay, first of all, I extend the deadline of the homework to next Friday. And so I will probably upload homework 3. So you can definitely not do it for sure now. So you can take a look at it. You should be able to do it the first of you, right? So yeah, and for the midterm, so midterm would be on Wednesday, right? So there will be probably one question on chapter 7 on how to compute the capacity, like what we discussed last lecture and in today's lecture. Okay, and then there will be like 5 problems overall, and the 4 problems will be on the previous chapters and the 1 problem on chapter 7. Okay, yeah, it'll be very basic, so don't worry too much about it. And it'll be easier than the homework. Yeah, unless you don't want, right? So. Okay, yeah, let's review what we covered in our last lecture. So in our last lecture, we start talking about chapter 7. Yes.
Are we gonna have class during like
Wednesday? No.
Okay.
Yeah, Wednesday there's no class on 25th. So this is normally what we do. Yeah, and but there will be a class on Friday. So let's say if the starting point is 9 a.m., then it will be due on 9 a.m. on Friday.
Okay.
You will have 48 hours. Yeah, it should not take more than 2 hours. I think if you're fluent with the concept, you can do it less than 1 hour. So, yeah, no class on Wednesday, but there's a class on Friday. Okay, so yeah, in the last lecture, first we talked about channel capacity. So we focus on the definition of the channel capacity. Right, and then we talk about examples on how to compute the channel capacity, right? The message we want to convey here is that although we know the channel capacity is a mutual information between X and Y, right? But we need to maximize it over all the possible input distribution, right? So this maximization may not be trivial. Okay. Right, and here's the definition of the, so first, in our last lecture, first we define the 3 kind of error probabilities, right? So the first one is the individual error probability, right? So basically, it's given by this formula, right? It means that given X is transmitted, and then what's the probability that the decoded message M hat, so that is not equal to N, right? So this conditional probability is called individual message probability of error. And then the maximum of it is called the maximum probability of error, right? So it's given by this. And then we have the average probability of error, which is the average of this guy. And from here, you can see that this is, so this one is the strongest, right? So basically, yeah, let's double check whether I recorded or not. Yes, I did. Yeah, the second one is the strongest. And so then the achievable rate is defined using the second error probability, right? So which basically means that, I say, if we have a Rn code, right? So you know what Rn code mean, right? Then for each n, so we're going to have a code, okay, or a code book, right? And when n goes to infinity, and the maximum error goes to 0, and then for this R, we say R is achievable. That clear? Right, so basically it means that for almost a 0 error probability, we have a non-zero R. Okay, so this is the definition, and it's pretty counterintuitive. And the capacity means that the supremum of all R, such that R is achievable. Right, the reason we have a supremum, not maximum here, is that so R may not be achievable exactly, right? So basically what we can show here is that any R minus epsilon for any small epsilon could be achievable, right? But R itself may not be achievable for a finite n, okay? So that's basically what it means. And then we introduce the Shannon's second coding theorem, which is the channel coding theorem. It shows that for a discrete membrane channel given by this, right? And then we can show that the capacity is given by the mutual information, and that is maximized over the input distribution. Okay, so this is a channel. So of course, this is a theorem, right? So we have to show it, right? So we're going to show it by the end of this chapter, right? But now we're going to show how you compute it exactly, right? Computing this is not trivial, okay? And we did the computation for the BSC and the BEC channel. Could you please, yes, for BEC and the BEC channel, right? And for the binary symmetric channel, we can show that capacity equals to 1 minus the binary entropy function, right? And for the binary error channel, we can show that the capacity equals to 1 minus the error here, right? Error basically is the epsilon, okay? And so we can see that we compute that using kind of different expansion of the mutual information, right? Because normally we have two expansion, two ways to compute the mutual information, right? One is hx minus hx given y. The other one is hy minus hy given x, right? So for the first one, normally h of x is easy to compute, but hx given y is not. And for the other one, hy normally is not easy to compute, but hy given x is easy to compute. Okay, so you're going to see this again. Okay, so in today's lecture, we're going to continue on this topic. So we're going to focus on the computation of the channel capacity. This is our lecture 26. So today, we're going to focus more on continue talking about examples. In particular, we're going to talk about symmetric channel. So we're going to introduce two kinds of symmetric channel here. Okay. And second, then we're going to focus on a more general way to compute the channel capacity, right? So we have seen a few examples already, right? But you can see that, so for each of them, it's kind of tricky to maximize mutual information, right? But we're going to show that there's a general way to maximize mutual information. Okay, so we call that an optimization theorem. Okay, so this is very, very important, and I don't think the book talks about that. So the reason we want to talk about that is that, so one of the reasons that, of course, we need that to compute the channel capacity. But the other reason is that when we talk about the very last part of our class, which is called the rate distortion theory, or the lossy compression, right? You can see that is kind of like the dual problem of the channel capacity problem. Okay, we're going to use something similar there as well, right? If you know this already, then we can, use something similar. We don't need to go over extremely details there. Okay. All right, and so this will be the agenda for today, and let's see how far we can go. So the first one is continue talking about examples. So we're going to go one step further to the general model. Okay, it's not most general model, but it's not very specific model. Okay, it's more general. So this is the third example we have seen here. So it's called symmetric channels. Okay, first we want to define the most restrict symmetric channel. It's called strong symmetric channels. Okay, so as you can see that for the binary symmetric channel and for the binary error channel, right? So we can represent the transition probability, using a matrix, right? So here, the symmetric channel basically means that the transition probability matrix is kind of symmetric, right? Let's see what do we mean exactly by symmetric here. So the transition matrix P, okay, so use this to represent the matrix, right? So with elements, so denoted by PRS given PR, Y equals to S given X equal to R, or PS given R, right? So does that look familiar, this notation? Where did we use it? Yeah, Markov stuff. And how about before that? When we talk about the we talk about the mutual information. Is that a cheat sheet?
Yeah.
Oh, they're very nice, right? So I suggest everybody doing this, right? Because we have so many concepts here, right? So writing down it is extremely helpful, right? It's very good, very nice. So anyone else did that already? Oh, really? Oh, really? Wow, this is surprising. Yeah, here I think the student from UF is really good. Yeah, so yeah, I have some comparison, right? So it's really, really good. Okay, great. Yeah, so we also talk about that when we compute the mutual information, right? If you remember, we're going to use that today, but if you remember when you say, okay, so if px, if this guy is fixed, then mutual information is a convex function of px. Sorry, concave function of px, right? And if px is fixed, and the mutual information is a convex function of this, right? So we're going to use the concavity of mutual information to compute the channel capacity, and then later on, after 10 lectures, we're going to use the convexity of mutual information using this guy to compute the rate distortion theory. Okay, it's very symmetric. Okay, so I think it's good to mention it now. Okay, so this is the element in each. This is the element in the matrix, right? And so we say, okay, so every row here is a permutation of the first row. Okay, so it's called, this is called symmetric, right? But meanwhile, if every column is also a permutation of the first column or any other column, so then it's called strong symmetric, right? So we have, if each row is a permutation of any row, and each column is a permutation of any column, so it's called strong symmetric, right? By the way, so for this kind of matrix, it's called doubly stochastic matrix. So, I don't know whether you heard of this or not. If you see random process, maybe you see that before.
It's in the homework.
What?
It was in the homework.
Oh, okay. Obviously, yeah, I didn't pay much attention to the homework, but so it's called doubly stochastic matrix. Okay, great. Okay, let's write it down. So if this matrix has the property that every row is a permutation of the first row, and every column is a permutation of the first column. Okay. So then it's called a strong symmetric matrix. Okay. And for example, let's say if we consider a BSC channel that we have seen before, the permutation matrix, the probability transition matrix is given by what? 1 over epsilon, 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 1 over epsilon, right? So here 0, 1, here 0, 1, right? And clearly, so every row is a permutation of the first row, and the second column is a permutation of the first column. Therefore, this guy is symmetric or strong symmetric, right? So this is symmetric.
I have a question or something.
Yes.
Why do they call this symmetric if the matrix itself is not going to be necessarily symmetric in the.
No, it's not. Yeah, so it's not symmetric matrix, obviously. I don't know why it's called symmetric. Yeah, no idea, just call symmetric.
Okay.
Yeah, you can give a different name, right? So basically, the only thing I want to make sure here is that, the row is more important than the column, right? Because by nature, it's a probability, so the sum of each row will be 1, right? So if each row is a permutation of any other row, so this, we just use this property. Okay, so we're going to use the column property a little bit. Later on, we're going to see that. But that's how it works, right? I think the reason it's called symmetric is that, so this basically means that, the probability will be somehow, how can I say it? You can see, so for example, if it's a binary symmetric channel, right? So it's like this. 0, 1, 0, 1, right? And from the first one, so the probability here is 1 minus epsilon, epsilon, right? And from second one, so here is 1 minus epsilon, epsilon, right? So it's kind of like symmetric, right? Because so every edge will have pretty much the number appear before for the first one, right? But it's a symmetric on this sense, right? So that makes sense, right? But the important thing is that every row is a permutation of, so all the number shown here, it has to be shown here, okay? So that's the most important thing. Okay, and for the BEC that we have seen before, so it is like this, right? So I have 0, 1, and I have 0, error 1, right? So this is given by this kind of thing, right? And we have minus epsilon. Yeah, so maybe if, before we use everything the same, right? So let's say, for example, if we consider a more complicated case, right? So I don't know whether it's called BEC or not. Maybe we just, it's a generalized version of BEC. Let's do not call that. So let's say, so if it's a combination of BEC and BSC, right? Let's say if we have another probability going from here to here, okay, and another probability going from here to here, right? And then, so we're going to, let's say, on this edge we have a probability of delta, right? And then we can see that, so here is 1 minus epsilon minus delta, here's 1 minus epsilon minus delta, and here is epsilon, and here is epsilon, right? So this is a combination of BEC and BSC, right? So BSC plus BEC. Okay, in this case, if we want to see what is the transition probability look like, so we can see that here is 0, 1, here is 0, E1, right? So basically here we have 1 minus epsilon minus 1 minus delta minus epsilon, epsilon delta, and the delta epsilon 1 minus delta 1 minus epsilon, right? And you can see here, so clearly, so each row is a permutation of another row, right? But for the column, it does not satisfy the definition, right? Therefore, it's called weak symmetric, weakly symmetric. Okay, and this is also a very typical channel, and we're going to have a way to compute this as well. Capacity of, you can see, so this is a bit harder than the previous case, right? And we're going to see how we can do this. Okay, so let's compute the capacity of the strong symmetric channel. Okay, so strong symmetric channel. Okay, in that case, capacity C equals to the maximization over Px and the mutual information, right? So let's see. So we kind of have seen that before, right? Let's recall this and see whether we can generalize it to any strong symmetric channel, strongly symmetric. Yeah. I suppose. Do that. Okay, yeah, let's compute it. So yeah, let's do it in this way. So you'll see why we can do it in this way. Okay, so if we expand in this way, as we said, computing entropy of y is not easy, right? It depends on the input, the distribution of x, right? But computing that is very easy, right? What is that? So given x, what is the entropy of y? So that is, yeah, because it's strongly symmetric. Oh, sorry, not strong yet, but because it's symmetric, right? So for each row, it's going to be the same thing, right? Therefore, it will be equal to the entropy of each row here, right? Because they are all repeating. Okay, so let's say if we denote every row here as R, okay, And then, so we can denote this as hy minus hr. Okay. Okay, and hr is very easy to compute, right? Very good. Okay, so now let's see what is the upper bound of it, right? As what we did in our last lecture, so we use the cardinality bound, right? So cardinality bound. To get log cardinality of y minus hr. Okay, very good. And so now we just need to make sure that so this equality can hold, then this will be our capacity, right? But what we tried before is that if it's a symmetric channel, we let x to be a uniform distribution, and then we can compute y is always a uniform distribution, right? But that may not hold in general, okay? But for doubly symmetric channel, let's see whether it holds or not, okay? So that's the idea. So yeah, so this equality will hold if y follows a uniform distribution. Follows a uniform distribution. Okay, so now there's only one thing we need to check for doubly or for the strongly symmetric channel. See whether if x is uniform distribution, whether or not y is also a uniform distribution. Okay, so that's the idea. So we let x follows a uniform distribution. Okay, and then let's compute y. Okay, then what's the probability of y here? Right, so that equals to this py given x px. Right, that's the total probability formula. Okay, so now we know x is a uniform distribution, right? Let's assume this equals to 1 over the cardinality of x, right? And that equals to 1 over x sum over all the x, right? Not all the y. Yeah. So here's a typo. All the x and the py given x. Right now, we need to be super careful on this term, right? So here, it's kind of a weird term, right? So summation here is over x, not over y, right? If the summation over y, then this term is 1, right? It's good, right? But now the summation is over x, right? So normally, what's the value of it is now known, right? It's unknown, right? But now, remember, we're considering a strongly symmetric channel. So basically, it means that for this kind of matrix, so the summation of all the row would be the same, right? Because each row is a permutation of any other row, column, right? So each column is a permutation of any other column, right? Therefore, the summation will still be the same, right? The summation is the summation of each column. Okay, then we know this guy will be equal to some constant number c here, right? So what number it is, we don't really care, but as long as it's not changing, then we're good, right? So this is equal to c over x, right? So this is not a function of y. Therefore, y is also a uniform distribution, right? Y is uniform distribution. Okay, then the capacity c here is nothing but log cardinality of y minus hr. Okay, so that's the capacity for the strongly symmetric channel. Okay, you can see that here, right? So we do use the symmetric property on the row, right? Each row is a permutation of any other row, so we use that, right? But for the second one, for the column one, so actually, in order to satisfy that, we do not need any column. It's a permutation of any other column, right? So what we need to guarantee here is that the summation of all the numbers for each column are the same. Then we're fine. Okay. Yeah. So this is the capacity for the strongly symmetric channel, right? So now we see the weak symmetric channel case, right? So kind of mentioned that already. So here, the official definition of weakly symmetric channel is that every row of P is a permutation of the first row. Okay, and if we just continue our just using the exact same approach as before, so what we can get is the follows, right? Hy equals to HR, Hy minus HR, right? So we can still get here, okay? So but now what is tricky is that, so if it's not, so for column permutation requirement does not satisfy, then how can we compute this guy, right? So basically, that's the idea. Okay, so let's see how can we get compute this guy, right? So we consider a particular example, right? So consider a channel look like this. It's an additive noise channel, right? Let's assume that here is the input, and then what the channel does is that we add a noise here, right? And then so we have an output. So it's called the additive noise channel. Okay, but it is, here we consider everything is discrete. So the distribution of Z can now be like a Gaussian distribution that we have seen in communication theory, in communication system class. Okay, so here we consider everything is discrete. So basically we consider this addition is a modulo addition. Does that make sense? So it's basically like if it's modulo 2, it means that 1 plus 1 equals to 0, right? If it's modulo 3, it means that 1 plus 2 equals to 0, and so on. So can we do modulo 4? We cannot. So we can do modulo 5, modulo 7, but not modulo 6, right? It has to be a prime number. Okay. Okay, so yeah, let's see. Let's define it officially. So a discrete memoryless additive noise channel is defined as, so we say X and Y. So the set of X and set of Y are the same. So they are in a finite field. It's called FQ. Okay, so FQ basically means that, so by the way, do you know what is a field? Right, field is, you definitely know what is a real field, right? All the real numbers, so it is a real field, right? So, this kind of algebraic concept means that, so you need to define a bunch of numbers, in a field is like a very big set, right? Or let me say this, okay? So there's like a step definition, right? In number theory, so first we have a set, right? Set is a bunch of numbers in the set and without any ordering and so on, right? And then, so if let's say we introduce a operation there, right? For example, if we introduce addition, right? We can do some addition in this set, right? The requirement is that if you do addition of any two numbers in this set, and then the result will still be in this set, right? Then it's called a group. Okay, so group is a bunch of numbers and with the addition operation, only one operation. Of course, you have addition, then you have a minus, right? And if we consider, okay, how about we have another operation, which is called multiplication, right? But no division, only multiplication. Okay, multiplication division is kind of tricky. Okay, and if we introduce another operation, so which is multiplication, then this kind of set is called what? Ever heard of it? It's called a ring. Okay, and then if we introduce addition, division, right? Then it's called a field. Okay, a field is a kind of a set. We have the definition of addition, multiplication, and division, right? And all the operation will result in a number in the field. Okay, this is for example, in the real field and the complex field that we're familiar with, right? We can do addition, multiplication, division, and the number, the result will be in the real set, right? So, yeah, it's not that complicated concept, right? Just need a little bit knowledge of it. So we use, for information theory, we use this finite field all the time, right? And normally in practice, let's say in most of the machine learning application, for example, we just use a real set or a complex set, right? In machine learning, just a real field, okay? But the application of finite field is that when we do the cryptography, right? We do this finite field. Now you can see what is the benefit of doing this finite field thing. So it's a modulo thing, right? So if the number is too large, then we're going to map it back, right? So then this will give you some, it will make your guess more blurry somehow. Okay, so I'll not go too far from it. So then basically, this conditional probability is induced by the random mapping yi equals to xi plus zi, and this addition is mod q, right? Which means that if this guy equals to q or larger than q, so you need to minus q, okay? So that's basic. And if it's below 0, then you need to add a q, right? So any number, this number has to be between 0 and q minus 1. Okay, great. And then from this, we can compute py given x. So it follows that the probability of y given x, so equals to, because we have this relation, right? Y equals to x plus z, then probability of y given x equals to what? The probability, so y equals to x plus z given x, right? So this is basically equals to what? The probability of y minus x, and equals to probability of z. Okay, yeah. Don't know. That clear? Right. So this basically means that the second term in the entropy in the mutual information is very easy to compute. Right. It's basically the entropy of z. The entropy of R is just the entropy of z. Okay. Very good. Okay. And also this means that this channel, defined in this way, is symmetric. Right. Because no matter what x, y is, no matter x is, right, the distribution is always this distribution of z. Right. The same for all the rows. Right, doesn't matter what's the value of x here, right? So this does not depend on the value of x, right? So therefore, hence this additive noise channel over a finite field FQ are always symmetric. Okay, and the capacity, therefore, the capacity is given by log Q minus HZ. Okay, so we can verify that. So basically, the first term can also follow uniform distribution. Okay. Very good. So this is a computation of some special case, right? So next, importantly, so we need a general optimization theory. Okay. So now let's see in general, how can we do the maximization of mutual information? Okay, so in order to do that, so we need to write down, so let's see, what is the structure of this maximization problem? So I want to maximize the mutual information, right? Let's write it down. Let's write it out, okay? So basically, E equals to summation over xy, and we have pxy here, and then log py given x divided by py, right? So this is the definition of mutual information. Right now, let's use our own notation for this, right? So basically, what we get here is that summation over all xy, and this first term, we can write this as this one, right? Okay, and here, for this guy, so you can see that, so this guy we know, right? So this is like P RS, right? And this guy is PR, right? And this guy is PRS, right? But this guy we are not sure, right? So PY. So we can write this, just using the total probability formula that equals to summation of x prime, px prime, py given x prime. Okay, therefore, you can see that, so this guy, so it's basically kind of PR, right? And this guy is basically PRS. Okay, and of course, if we consider this is a PRS, then PRS is, is hidden here, right? So one of the term is PRS and times PR. Okay, so that's basically how we can see this, right? So now, so what we're going to do is that we're going to compute the maximization of it respect to PR when PRS is fixed, right? Because PRS is the channel model, right? So that's fixed, and then we just need to find, okay, so what is the value of PR that can maximize it, right? And for all, x, right? Okay, and as we said before, so this function is a concave function of PR. If it's concave function, right, then we can use the convex optimization technique to solve it. Okay, so let's write down this optimization problem here. Okay, so we need to do the maximization of it, right? And then we need to consider a few conditions here, right? So we need to subject to that summation of px is equal to 1, right? And then we need to make sure that px is between 0 and 1 for all x. Okay, so this is basically our optimization problem. Okay, and then here we can see that, let's rewrite it a little bit. So this is equivalent to say that we want to do a maximization of P and P single bar and P double bar. So this is PR, the vector of PR, and this is a matrix of PRS, right? So we introduced this notation before when we talk about mutual information. Okay, so we can view the mutual information as a function of PR and the PRS, right? But PRS is fixed, right? So this will equals to something like this. So we sum over R, and we have PR sum over PRS, and sum over PS, right now PRS and RS, and then we have a log in the upstairs is PRS and downstairs. So here is already here. So here is summation of R prime, PR prime, and PR prime S, right? And subject to that the sum of all the PR is 1, and for each R, PR is in 0 and 1. Okay, so basically this is the optimization problem that we want to solve. Okay, so any questions so far? No. Okay, great. Okay, so now let's consider how we can solve it, right? As we said before, so what we do know is that, so this function is a concave function of P, right? P is the vector PR, okay? Therefore, let's say if we denote this optimization problem as star, then we know the star is a convex optimization problem. Okay, so yeah, it can be concave or convex, doesn't matter, right? If it's concave, then we'll do a maximization. If it's convex, then we're going to do a minimization, right? For both of them, it's called convex optimization problem, right? How to solve it? So who had learned the convex optimization before? Yeah, how to solve it? A general convex optimization problem. Yeah, gradient descent thing, but we cannot only do gradient descent on this, right? Because we have a constraint here, right? If there's no constraint, you just do a gradient. I mean, the computer gradient, let it go to 0. I mean, let it become 0, equal to 0, and then we can get the optimal solution, right? But now we have this constraint here. What should I do? Yes.
Aren't it like the KKT rules?
Exactly. Definitely. We're going to use the KKT condition.
Multipliers?
Yeah, exactly. Yeah, we're going to use the KKT condition. So what it does is that we convert this problem instead of the following problem, right? So we're going to maximize this guy minus the Lagrange multiplier lambda, and then so we're going to write here the condition here, right? So basically, this is this condition, right? So this minus 1 equal to 0, okay? So we also need to do these two things, right? But here it's too simple, we don't need to do that. So we do that will be enough, okay? So we call that JP, right? And then we can solve this from subject to PR bigger than or equal to 0, okay? Then it'll be enough. Okay, so let's see so why it will work, right? The idea is as follows, right? So if for a concave problem, so a good example of a concave problem is a quadratic function, right? So basically, let's say if we have this kind of shape, okay, and then here is 0, and then here is our function fx, right? So in this case, you want to solve the problem. Let's say, so then this will be our solution. So that's our P, or that's our x optimal, right? If we use x, okay, then we're good, right? So then, let's say if we have this case, right? So we basically do not, so we're good, right? So if we can, then if in this case the gradient of I will be equal to 0. Okay, and then we just need to do a gradient of this, we're fine, right? But if this point is not in the range of 0 and 1, right? For example, if this guy the shape is like this, and then we're not so good, right? So because this point is below 0, then it's not achievable, right? But only this point is achievable, or this point, something like that, right? But for this point, so for this point, it does not equal to the point corresponding to the gradient equal to 0, the gradient of this equal to 0, right? But it corresponding to what? The gradient of fx is less than 0, right? That true? Yes, right? So here we don't need to consider, the upper bound of 1 here, right? If it does not satisfy that, we just normalize it, then we're fine, right? It's not too important. But this is important, right? So if the optimal point is at below 0, and then, so for this point, we know that the gradient is less than 0. Okay? So basically, by using this tool, so we can solve this analytically, right? Solving this is not hard, right? We can always use the KKT condition to solve it, okay, without any problem. But what is difficult is that, so is that possible that we can get a closed form solution? right? That will be much more convenient and can see more insight, right? That is what is challenging, right? Our goal is to get a closed form solution. Does that make sense? Okay, so it turns out, this is just simple form for the, single variable function, right? It turns out that we can generalize it to the vector case, okay? So let's introduce a theorem here. So let's call this theorem double star. So let fx, fx1, fx1, x2 until xn be a concave function. Suppose that the max is over all of them is bigger than 0. Okay, and so on. And then this function is achieved by x1 equals to x1 star, x2 equals to x2 star, and so on until xn equals to xn star. So this is the optimal point, right? And then if x star, x1 star is bigger than 0, right? Which means that, so the optimal point is bigger than 0, right? It means that it's achievable. Then, achievable, what I meant is that the 0 gradient is achievable, right? Then this, let's say xi, not x1. So this guy, I should use this notation. Xi equals to xi star. So the gradient of this is equal to 0, okay? But if xi equals xi star equal to 0, and then this guy will be what? Less than 0, okay? Like what we have seen here, right? So if this guy is not, this point is not achievable, then the gradient will be less than 0. Okay, because it have to go down. Okay, very good. Okay, let's see. Okay, then, so let's go back to the KKT condition, right? So now we're going to do a derivative of JP, right? So we can see that the derivative of JP, we do that with respect to PR, one of the elements here, right? Then it will be equals to this. And then minus lambda, right? So here, so if we do a derivative with PR, so this one will disappear, and then only lambda will stay. Okay, very good. So any questions? Okay, then, so therefore now we only need to compute the first part, right? So let's compute that. P double bar, PR. Okay, and so this computation is kind of complicated. So let's see whether we can do this or not. So we need to write down what we got before. Okay, so PRS downstairs is summation R prime, PR prime, PR prime S. Okay, so now we do a derivative of this guy with respect to PR, right? So we can see here's a PR and here's a PR. We have a PR here, right, downstairs, right? So this multiply that, then we need to use, the rule is that we do a derivative on this guy, multiply that, and then then we use this multiply derivative of that, right? That makes sense. So basically, the first step is that we need to do a derivative of this guy, okay? And then we only have one R left, right? And then summations over S, well, PRS log PRS divided by PR prime, PR prime, PR prime S. Right, because just one PR here, right? The derivative of that is 1, then multiply this guy. Okay, so that's the first term. Right, the second term is more complicated, right? So the second term is that if we do a derivative of that, then it's a log, right? So just consider here that we just consider it's a ln, so that will be easier. later on, because we're going to let this guy go to 0, right? It doesn't matter for a constant difference, right? Then we just need to compute 1 over this guy here, right? So yeah, let's write down the constant in front, PR. Yeah, PRS, and then we need to compute the 1 over this guy, right? So that is R prime, PR prime S, PR prime, and PRS, right? And then, so this is the derivative of this guy, right? And then we need to do the derivative of what is inside, right? And the variable is downstairs, right? Then what we need to do is that the downstairs, which is this guy, square, and then we do a derivative of this guy, and we have a minus sign here, right? So that's PRS. Okay, and now let's see what is that, right? So basically here, a lot of things can be canceled. Okay, so this and that can be canceled, right? And this and this can be canceled, right? And then, so this will be also canceled. You can see many things can be canceled here. So then what's left here is nothing but this guy. PR prime S plus minus 1. Okay, because everything is canceled here. Okay, and then for this guy, we know that equals to PY, right? So now let's write it down. So what we got here is what? So basically, remember what is S here? S is Y, right? R is what X equal to, S is what Y equal to. We basically, if we want to write, using a more readable term, is PY given X equal to R. And then we have log upstairs is PY given X equal to R divided by PY minus 1, right? And over time. So basically this guy will equal to what? Right, it's almost a mutual information, right? But difference here is that we have mutual information between X equal to R and Y. Okay, so then this is what we got. Okay, therefore, we can see the derivative of this guy with respect to PR equals to the mutual information between X equal to R and Y minus, so I have minus 1 here, right? And before, we have a minus lambda here. Okay. So this is a very nice formula. And what we're going to do is that, so basically, we are going to let this guy go to 0, right? But we need to use this theorem here, right? So the optimal solution is here, then this will be equal to 0. Otherwise, it will be less than or equal to 0. Okay? So basically, let's write down the last sentence here. So what we are going to do is that using theorem, double star, then, so if this guy is bigger than 0, then this guy will be equals to 1 plus lambda. And if this guy equal to 0, then this guy will be less than or equal to lambda. Okay? Yeah. Yeah, let me finish it. So then we can compute the channel capacity here, right? So that's basically equals to the mutual information between Px, y, and we know here is the optimal condition, right? So basically that equals to R, summation over R, PR star, right? And then it's the mutual information between X equal to R and Y. Okay, and here, so we're going only to do the summation here that such that it's bigger than 0, right? If it's equal to 0, then it will have no contribution, right? Okay, and then PR star. So then it equals to R, PR star bigger than 0, PR star times 1 plus lambda, right? And we know 1 plus lambda is a constant, and this guy will equals to 1, right? Because it's just all the probability. The only thing we ignore is PR equals to 0, right? Then it equals to 1 plus lambda. Okay, so that's basically the channel capacity, equals to 1 plus lambda. Okay, so next class, we're going to talk about the implication of it. What does that mean, right? Because we don't know lambda, right? Okay, great. Thank you.